Alright, so for our last problem, we now have our inclined plane set to 35 degrees, so we know the brick wouldn't stay on there by itself, but it's being held on by a string. And this brick is in equilibrium, and how do we know it's in equilibrium, Stacy?
It's not moving.
It's not moving. So what we're going to do is calculate how much tension must be in that string to keep it from sliding down. Okay, so for this problem, we still have our normal force perpendicular to our inclined plane again. We actually drew it on the brick. So we have our normal force perpendicular to the inclined plane. The weight is still straight down. And then of course we have a string attached to our brick, so we're going to have tension going this way. Now this is actually an interesting problem. I attempted to set it up by just letting it down until it would stay, so that I have Fs max working in the same direction as the tension. So it's like the friction and the tension are working together to keep it from sliding down the plane. But in theory, it would be possible to have the tension so great that it would pull it up the plane and that the friction's actually keeping that from happening. So it's going to be tough to get a correct value for this problem, but hopefully it will come out close. So we are assuming that the tension and the maximum static friction are actually working together for this problem, and I don't know why that just moved. Alright, so at any rate, let's go on to the next page and we'll get that set up, taking a look at this free body diagram right there, but ignoring this green friction. So here's our free body diagram showing the four forces that are acting on the brick, assuming that I really got an Fs max going to the left, which is what I tried to do. So I'm going to break that up into components. Once again, I'm going to leave the normal alone. I'm going to leave the tension alone. I'm going to leave the Fs max alone. But I'm going to take my weight and I'm going to split it up into mg cosine theta going opposite of the normal, and mg sine theta going parallel to my plane, kind of down the hill. So what we see then is that the normal force has to equal the mg cosine theta, and we also see that T plus Fs max should equal mg sine theta. Okay, so we're trying to solve for our tension, but what we are going to need to do is plug in for our Fs max. So remember that Fs max equals mu Sn, so then I can say T plus mu Sn equals mg sine theta. But then we've said in this equation right here that n is the same thing as mg cosine theta. So then we can say that T plus mu S mg cosine theta should equal mg sine theta. And so then by subtracting I can solve for t and get that t equals mg sine theta minus mu S mg cosine theta. So let's plug in our values and let's see what we get. So t is going to equal 1.5 times 10 times the sine of 35 minus mu s, and remember on the last problem for mu s we came up with 0.51 times 1.5 times 10 times the cosine of 35. I apologize, I'm running out of room there. And let's see what we get for our tension. And assuming that I put everything in the calculator correct there, I got a tension of 2.3 newtons. So assuming we were getting the maximum force of static friction possible, which still would not have been enough to keep the brick from sliding down the hill, because remember the maximum force would only hold it at 27 degrees and we were at 35. This says that we're going to need a tension of 2.3 newtons to work along with that maximum force of static friction. So let's check out the video and see if I really got it set up right and it comes out pretty close to 2.3 newtons. Okay, so now that we've calculated the theoretical tension, Stacy, can you tell us how much tension is in the string?
4.8.
4.8 newtons. Thank you, Stacy. Okay, so Stacy told us that the tension in the string was 4.8 newtons, and basically what that tells me is that for whatever reason, I was not getting the maximum possible value of static friction there. So tension was doing a little more of its part, and then static friction was doing a little bit less than the maximum it possibly could. So really our physics is still kind of verified there. The only way that we really would have kind of disproven our math was if she had gotten a value that was less than 2.3 newtons. So, not surprising that it didn't work out exactly like I wanted to, because it's hard to set it up to make sure you're really getting the maximum friction and the minimum tension possible.